Okay. Please welcome, we're very lucky to have Vince coming here, so please welcome Vince.
Hello, everyone. Thanks for having me, and well done to Casper and Tim for getting to the 10th meetup of PyData. It's fantastic that it's going so well and to have such a huge amount of people as well. So my name's Vince. On Twitter, I'm Dr. Vincent Knight. Some of the stuff I'm going to be talking about today, you can actually see in this preprint here on the archive. If you want to, or you can just speak to me. A bit about myself that hasn't been mentioned already. I'm a mathematician at Cardiff University, and some of my research interests are in game theory. I also get to teach all our first-year programmers programming, first-year mathematicians programming, to make them programmers, which is probably the bit of my job that I enjoy the most. I'm a fellow of the Software Sustainability Institute. So the Software Sustainability Institute is a UK institute funded by research councils that are all about promoting the correct use of software in research. There is a lot of research that is done today that simply is not reproducible because the code to do it was badly written, doesn't exist anymore, is locked away somewhere that someone can't have access to. And so that idea of, yeah, here's a link with our code, good luck downloading the postdoc that wrote it, that's kind of what the Software Sustainability Institute is trying to get away with. And that's through education of academics, because, for example, mathematicians, we're not necessarily software engineers, but we have a lot that we can learn from software engineers, and there are various other disciplines for which that's true as well. As part of my interest in the robust and sustainable use of software in research, I'm also an editor for a journal called the Journal of Open Source Software, and so it's a research journal that's mainly put in place to ensure that it's possible to get credit for writing research software. Nowadays, really, the paper is often not actually the important part of the research. It's actually the software that was written to be able to write the paper. And so there are lots of journals that are turning up nowadays that aim to still use the old currency of papers to give credit to the new gold of research, which is the software. And then finally, what I'm going to talk about today is game theory. So this is a logo that myself and the other developers of a library for game theory came up with, and we thought it was fantastic. So you actually use the library to write the logo. And then over the past couple of years, I've realized it's a terrible logo, because if you look at the three logos, it doesn't look like a logo. It tells you absolutely nothing about what it is. So you'll hear the name of it as we go, because some of the research I'm going to talk about today it uses it. So I'm afraid there's going to be some level of participation. It doesn't need to be much, and you can just keep staring at your computer to send a signal to the person next to you that you're not interested in participating. But what we're going to do is play rock, paper, scissors, lizard, Spock. Has anyone never heard of this game before? Put your hands up if you've never heard of it before. Fantastic. I believe most people will have heard of rock, paper, scissors before. Is that true? So rock, paper, and scissors, right? It's Rochambeau is another word for it, and it's just a circular game where one of the things beats the other. And then rock, paper, scissors, lizard, Spock is just another version of it, where so paper covers rock, as it always does. Rock crushes lizard. So if you're going to participate, practice doing these symbols. You'll see why in a little bit. So this is a lizard. Go ahead, everyone, if you're going to play, do the lizard. Thank you very much. And then the lizard poisons Spock. Now, I do this in my final year game theory course, and someone should do a study on it. Not everyone can do this. So find out if you're able to do this. Make sure it's different to this. Make sure it's different to this. This and this are different, and that's important because paper's this, and this is Spock. So if you're unable to do this, because, for example, it looks like that, or like that, just keep that to yourself because you're about to play. And if I happen to know that you can't do this, then it gives me a slight advantage. All right. Then Spock smashes scissors. These are scissors. And then finally, scissors cuts paper, and there are various other things in between, such as Spock vaporizes rock, scissors decapitates the lizard, etc., etc. All right? So the way this game is played is exactly in the same way that rock, paper, scissors is played. So you go 1, 2, 3, and you make a choice. Spock if you're able to. Don't choose Spock if you're not. And then the opponent, you play against someone. So if you haven't spoken to your neighbor, you still don't have to speak to them. You just have to use your hand signals with them. Does the same thing, and then you look at this and you find out who wins. Okay? So what I'd like you to do is, for a certain amount of time, go ahead and play. So with the person next to you, just play. All right. Put your hands up if over all the games you played. Put your hands up if you won. Yeah? Okay. Someone want to yell why you won? You cheated? No, that's great. That's great. I didn't tell. How did you cheat? So someone just yelled out that they cheated. How did you cheat? Oh, okay. So how did you win? Sorry. Pardon me? You only played rock the entire time, right? Yeah? Fantastic. And so a lot of the time your opponent played lizard. They're probably trying to be fancy, right? And what was the other one that rock beats? Scissors, right? So I'm guessing. Yeah? Did they play paper at all? And then you just kept with it, yeah? Anyone else? Yeah? Spock vaporizes rock, right? Ah. Okay. 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 Right? You have to hide that. If you can't do Spock, you want to hide it, right? Yeah. So someone over there, let me summarize and paraphrase a little bit of what you said. You got in the mindset of your opponent, figured out what they were going to do, and realized that rock was probably a good thing, right? Anyone else? Ah, stop the game while you're in the lead. Yeah, that's very smart. You got in the lead by playing what? You just picked something, yeah? Anyone else? You played against yourself. Okay, I think that means you tied. All right. Alrighty, so do we think that's the winning strategy? Do we think that you should just play rock all the time? No? You did lose eventually, but overall you won, right? Does anyone want to suggest how you should play? Uniformly. So uniformly as in you just cycle? With uniform probability. Yeah, so being able to play randomly. All right, so this is the sort of stuff that I'm going to talk about today, and essentially the mathematics behind the strategic decisions that come about when we play something like this, or as we will see, perhaps something a bit more useful. So there is a Python library for game theory. It's called NashPI, and it's named after a mathematician called John Nash. Some of you might claim I'm wrong for calling him a mathematician, but I have the microphone, so we'll claim him. And it allows you to do various things. So let me just make this a bit bigger. I've input some of the things already just because I don't want to have to do it. So let me make this a bit bigger. What you see there is a mathematical representation of rock, paper, scissors, lizard, Spock. All right, it is ties along the diagonal because rock ties with rock. And then if I knew the description of the game, a 1 means whatever that row is beats that column and beats that column, etc., etc. So that's a way of representing the game you just played mathematically. And then what we can do with that is we can create the game. Oops. By just passing it to a NashPI game, and so it's a zero-sum game, and zero-sum is just game theory for if I win, you lose. All right, there's lots of games where it's not like that, where we can both win, but rock, paper, scissors, lizard, spock is a game that if I win, you lose. So it recognizes that, and it has the different scores for the two players. And what we can do, so for those of you who only played rock, right, and whatever else some of the techniques it came up with, if you started playing again, especially after we had that conversation, your opponent would probably change, but you might preempt that change and change as well. And what would happen over time is our population would learn. And if things got really, really dramatic, and if you lose, you die, then we'd really try and learn fast, right? Well, NashPI has algorithms for this, so no one has to die. Let me just. So what I've done there, that's taken absolutely no time at all, because what NashPI only uses is what are called Python generator objects. And generator objects are absolutely wonderful things within Python because they are just an encapsulation of instructions for doing things. You can write an infinite loop as a generator that doesn't break your computer. So once we have that, I can just plot it into the plotter, and this is some other code that just rips out the answer, the various play counts over time. And what we get is this. Now, I realize there's no axes on these labels, and sorry, no labels on these axes, and not everything is completely clear. But again, I'm the one on the microphone, so it doesn't matter. What we're doing is essentially playing and learning. So every iteration, we've gone, right, what is everyone doing? Everyone's playing rock, so I'm going to adjust and I'm going to play Spock. All right, and then, oh, now everyone's playing Spock. What am I doing? And over time, we start oscillating very, very close to the uniform distribution that a few of us talked about earlier. And so that's what NashPI can do. It can do, that's a particular learning algorithm called fictitious learning, and it just essentially makes everything rather dramatic and just lets the mathematics go and see what would happen in population. But that's not actually what John Nash did. John Nash actually found something else, which is called a Nash equilibria. And so NashPI lets us find those as well using various algorithms. One of them is called support enumeration. Oops. Sorry, I'm doing this one-handed and that's slowing me down. And so that's also just theoretically calculating what everyone should get, which is indeed both players uniformly playing a fifth, a fifth, a fifth, a fifth, all right? Which is what you should do and what we see a population learning to do. Really interestingly, that's not always the case. Some games, if you just see what happens as you learn them, you don't converge to these theoretic equilibria. You go somewhere else, which is kind of interesting because it adds a whole theoretic debate about what is a Nash equilibria. But that's one bit of game theory. And what I'd like to talk about now is something a bit different. So what I'm going to do is I'm going to play this YouTube video, which probably will have sound. It seems like I might actually have the right number of ports remaining on this computer for you all to hear it. Who has seen this video before? Okay. Don't spoil it for the person next to you, right? All right, let's see if this works.
This.
Right, so it works. So a brief introduction. This gentleman's going to explain it as well. It's a game show. These two people have spent the last hour or so playing together as a team to get a bunch of money. All right. So they've gotten £100,000. Okay. And now they have to decide how and if they share that. All right.
Is serious, life-changing money. Your jackpot today is £100,150. You have one final decision to make. Easy decision. We're now going to play split or steal. I know you're the last two people in the country I have to explain this to. But you have two final golden balls. You each have a golden ball with the word split written inside. You each have a golden ball with the word steal written inside. You will make a conscious choice of choosing the split or the steal ball. If you both choose the split ball, you split today's jackpot of £100,150 and you go home with £50,075. If one of you splits and one of you steals, whoever chooses the steal ball will go home with £100,150. And the person who chooses the split ball goes home with nothing. If you both choose the steal ball, you go home with nothing. Okay. Before I ask you to choose, I want you to look at your two golden balls and make sure you know which is the split ball and which is the steal ball. This is very important. Make sure you don't show each other. Before I ask you to choose, I think you have some talking to do to each other.
Stephen, I just hope they weren't puppy dog tears and they were real tears and you were genuinely going to split that money.
I am going to split this. That's 50,000. I'm just, it's unbelievable. I'm very, very happy to go on with 50,000.
You were genuinely going to split.
If I stole off you, every single person there would run over here and lynch me.
There was no way I could, I mean, everyone who knew me would just be disgusted if I stole.
When people watch this, they're not going to believe it.
Please.
I can look you in the, Sarah, I can look you straight in the eye and tell you I am going to split. I swear down to you, I am going to split.
Okay. This is serious money.
It is.
Sarah, Steve, choose either the split or the steal ball now. Hold it up.
We're going on with 50 grand each. I promise you that.
Split or steal?
This is my favorite part, and she's about to turn away because she can't look at him. How many people saw that coming? Yeah. How many people assumed he was going to steal? Yeah. I think this video is really nice because I think it plays to some of our subconscious biases. How many people think she's right? Yeah. Whatever you prefer. What do you think? Okay. Why not? Why is she morally wrong? Because she can buy a lot better friends now, right? Sorry? Yes, yeah. That's right. And if you watch it carefully at the start, she's actually completely honest. She never says she's going to do anything at all. She's brilliant. And he's poor. So this game is what's called a prisoner's dilemma-ish. And it's a dilemma because if these two people work together, then the overall situation is better for everyone, right? Whereas if everyone works together, the one person can take advantage of that, right? And so obviously this game show is a bit artificial, but these situations, this prisoner's dilemma, is a fantastic model for all individual interactions we ever have. When we are at a door waiting for someone to come past, when we are just need to decide whether or not to be nice to someone, that's always a prisoner's dilemma. If we take it back to the evolutionary basis of cellular stuff, then you know, does a particular cell take over and fight for the food of all the cells, or do cells work to aim to work together? And so this prisoner's dilemma is a fantastic mathematical tool that's been used to explain not just, for example, there are models of cancer that are based on not this game show, but the game that this game show is based on. And there are also models of social interactions that are based on this same prisoner's dilemma. And the library that a few of us have mentioned today, the Axelrod library, is a model, is a Python library for studying the prisoner's dilemma. And we're going to go into that a little bit. As another example of how it kind of happens everywhere, this is a tweet that Dr. Kirsty Jean put up in 2017. So, me sets up flawless heat competition trial. Lizards will fight over hot podium. There can only be one winner. So, I don't know Dr. Kirsty Jean. I believe she studies lizards and their behavior. And the experiment she's describing, and there's a picture that's coming up now, is lizards are in a thing, a cage, a container of some sort, and there's a big rock in the middle that's hot. And lizards are cold-blooded, so they like the hot rock. There's only room on that hot rock for one of the lizards, so the lizards are going to fight, and one of them will take the hot rock. Maybe, and I'm completely making this up, maybe the idea was one of the lizards has a particular genetic marker on it, and you want to see if that marker always predisposes the lizards to win the fight, or something like that, right? And then this is what happens. The lizards share the heat. They go, let's just chill out together, all right? And so what's nice about this is that Dr. Kirsty Jean designed a system with very simple rules, with expected behavior, and what happened was not within the rules, was not what Dr. Kirsty Jean expected. This happens all the time. We build new roads, spend a lot of money on new roads, and then people don't use the roads, or people use the roads too much and traffic actually gets worse. That's something called Braze's paradox. It happens all the time. And so this is a prisoner's dilemma, right? Because the lizards were supposed to go, oh, if you're just going to chill out, then it'll be easier for me to fight you and take the heat, right? But in fact, the lizards didn't play the prisoner's dilemma as they were expected to, right? And so what the lizards ended up doing is cooperating. If we take that prisoner's dilemma model, we all are quite a cooperative species. We all work together, right? And, why is that? Because as you pointed out, if you think about it mathematically, you should take the money. You should fight the lazy lizard. You should go through the door first. So why is it that our behavior has evolved to not do that? And can we explain that mathematically? And the answer is yes, and we can use Python for that as well. So one model for this is to use something called a moron process. This is a mathematical model of evolution. And a moron process works in a relatively straightforward way. You have a population, and you have blues and reds, all right? If you're colorblind, you should still be able to see that the hash is going in different directions. But basically, you have two types of population. So a lazy lizard and an aggressive lizard, or something like that. And then what we do in this model of evolution is we select an individual that we're going to reproduce. And what we do is we select that individual according to their fitness in this population, all right? So if we have nothing but lazy lizards and one aggressive lizard, the aggressive lizard will be very fit for that population because they'll be able to take the heat away from all the lazy lizards, right? But if we have one lazy lizard in a population of aggressive lizards, then the lazy lizard probably won't do that well. Or if we have nothing but aggressive lizards, the aggressive lizards will all fight with each other, so they'll probably do even worse. So based on how well they do, they're more likely, essentially, to breed. So they're more likely to be selected to create another one like them. So we have another red one there. And then what we do is randomly, completely uniformly, not regarding how well they are fit to their population, we select one for death. And we keep repeating this procedure, and over time, with non-zero probability, you will either arrive at nothing but blues or nothing but reds. And that's when the process ends, and you're interested as when one of these behaviors becomes fixed. All right? So we have somewhat evolved to be a society that cooperates with each other. How did that happen? This is just some Python code to explain it, but I won't go through it. It's just explaining the process in code. My slides will be online. If it helps you to visualize it that way, you can. This is the game. So the same way that we had that mathematical model for rock, paper, scissors, lizard, Spock, this is the prisoner's dilemma. If both individuals cooperate, they both get a 3. If one cooperates and the other one defects, so takes the money, fights the lazy lizard, they get 5. If they both fight, they both get 1. And if you cooperate and the other person takes advantage of you, you get 0. And that's a very simple game. It's one of the first games you teach when you teach a game theory course. And there's not much interesting to say about that game, because what you say about that game is the exact same thing that the person over there said when we watched the game show, is mathematically, you should take the money, right? So both people should take the money. And that's all there is to say about this. Where this gets interesting is when you start repeating it, and where our interactions are not single-shot interactions, but are continuous building of our own reputation. So the reason I'm nice to you today, the reason I share my food with you today, the reason why I don't take all the resources available to us today is because hopefully you'll do the same tomorrow. And this was first studied in detail by a gentleman called Robert Axelrod in the 1970s. And what he did is he invited people to submit computer code that played that repeatedly played that game for 200 turns or a probabilistic number of turns. And the rules that you submitted, the strategies that you submitted, could take into account what your opponent did before. And the Axelrod library, which is one of the things which is one of the libraries of which I'm a developer, is a model. It does this. So you can put a player called tit for tat against a player who always cooperates, and you see that both players always cooperate. If you put tit for tat against defector, tit for tat starts by cooperating, the defector starts defecting, and then they both just continuously defect. And tit for tat versus alternator, you might now realize what tit for tat does if you don't know already. Tit for tat looks at your entire history of play, what you've done forever against me, ignores almost everything, just looks at what you did yesterday and does the same thing. So tit for tat is a strategy that wants to cooperate, but importantly will punish you, and even more importantly will forgive you. And this tournament that Robert Axelrod ran, he actually ran the first one, had 15 odd strategies submitted. He ran a second one practically immediately that had 64 strategies. And you have to realize when we say submitted, this isn't people opening pull requests on GitHub. This is people sending paper with Fortran code written on it that had to be rewritten. So 64 strategies was quite a lot. And both of these tournaments were won by tit for tat. And so this was deemed as a wonderful example of, look, we have a very simple model for why and how cooperation can occur, because tit for tat actually does well in these environments. And there's a lot of ongoing research, including my own, on this topic. And a lot of people still claim tit for tat wins the prisoner's dilemma. The prisoner's dilemma is solved, it's tit for tat. And that's kind of forgetting a lot of things, which I'll delve into a little bit now. So this is the moron process. And so, for example, if we have a cooperator and a defector in the population, and we start out with a population of 7 individuals with a single cooperator, we can see that over time, the cooperator can actually take over. But likewise, the defector could also take over. So probabilistically, we start to get interested in what can happen, what happens more often. What we did is we looked at a particular type of strategy called a finite state machine. So a finite state machine is just essentially a lookup table that encodes a certain amount of things. So it encodes a certain amount of previous moves by yourself, by the player you are, a previous amount of moves by the opponent, and a particular state. And this is essentially an abstract thing. You could also think of it of, are you happy right now? Are you suspicious right now? Are you suspicious again? But for intents and purposes, it's an abstract state. And it takes those three things, takes an input, so what your opponent did on the previous move, and moves you to the next state and gives an action. And what we did is we trained these using reinforcement learning. So there's a library called the Axelrod Dojo. I thought that name was great. That takes these strategies and essentially trains them. And so reinforcement learning is a machine learning technique where you essentially put something in an environment, you see how well it does, and then you modify it. And you continuously repeat this. And this is what our finite state machine, what these finite state machines look like. You don't have to worry about the details too much, obviously, but you see a number of states, and then based on the input, you have the output and which state you go to next. And our reinforcement learning algorithm, all we told it was that this was a finite state machine with 16 states. And then what the algorithm is doing at every step is essentially changing the symbols here or moving the arrows from one state to the next, all right? And so this just happened. We just put it in and let the model evolve to see what would happen. And what we did is we put it in this big tournament similar to Robert Axelrod's, but instead of just playing a match where they just played the prisoner's dilemma against each other, we put it in that evolutionary moron process. So we saw who would be likely to evolve, and we let the reinforcement learning algorithm essentially move those arrows, move those symbols to find what would be strong and have a good chance of evolving. And this is a table of some of the results, but we looked at whether or not you invaded or whether or not you resisted invasion. And being able to invade, the particular strategy I put up, so one that was completely written by a computer, is the strategy that won. So something that's able to take over a population was something that the computer essentially coded. We didn't. The various other strategies here, if you look long enough, you'll see that tit for tat is not there. This is the top 16. The tournament had more than 200 strategies in it. And what's particularly interesting about the strategy that did win, that finite state machine that evolved, is that if you take a close look against an array of opponents, so every row is a different opponent, and what it is simple. Every row is an opponent that plays randomly, cooperates with given probability. And what you can see is that the behavior of the strategy, so whether or not the strategy cooperates, changes, except for the first 3 turns. So this strategy, this finite state machine that evolved, always does the same thing on the first 3 moves. It cooperates twice, then it defects. And because it's getting late, I won't make you stare at this for too long. But what the algorithm did was essentially emerge the ability for the strategy to recognize itself. And so if you go through all this and you see what happens when you're playing against itself, if you cooperate, and defect, you end up down here, which you're in a state where as long as your opponent keeps cooperating, you will keep cooperating. So you have to defect, because it's the only way to send a signal. So you cooperate twice and then you defect. And then if your opponent also does that, you're in this place where you're like, okay, let's mutually cooperate for the rest of our time together. And what that is a secret handshake. It's the ability to recognize itself. It's the ability to realize we need to work together, all right? And that just happened all by itself with no input from us. We actually had to go understand what the strategy was doing because it came out as a bit of a black box. These strategies are trained with 164 strategies. That was at the time, that's how many strategies there were. And I'm gonna just about finish now, but one particularity of this project is that the Axelrod library, so the Axelrod's original computer tournament that was run in the 70s was written in Fortran. The papers he wrote had been cited hundreds of thousands of times. It's very much considered seminal work. The code that was used for it doesn't exist anymore. You cannot find it. A few of us are doing some work to kind of work against that. But this project, the one I'm describing, and this tournament, the actual library with the Axelrod code, just that anyone can pick up and use to run these tournaments themselves, is all on GitHub. And it's actually a wonderful project because to code a strategy is relatively straightforward. We've had lots of pull requests from people who've never written Python code, who've never done a pull request before, including Julie. And Julie did this as part of one of her courses in France, where their project was go contribute to an open source project. And so that's what they did. And I think by having contributions like those from Julie, we're essentially being able to have a much richer body of strategies than if 3 of us sat in our offices had done it. So this project essentially has more than 40 contributors who've made it a much richer experience. These are the co-authors of the paper. Here are a number of links. This is the slide. If you do want to take a picture of it, by all means do. Here's the preprint that I mentioned. Here's the GitHub repository. If you're interested in game theory as a subject, these are my final year game theory courses, which you're welcome to take a look at. And that's all I have to say. Thank you very much.